Thank you very much. So I'm going to give you a short introduction to Isomorphic Labs, who we are and what we're doing. So the company is based in King's Cross in London. There's about 220 of us now, and 20 people in Switzerland, in Lausanne. So I joined the company just over 3 years ago. I was employee number 15, so we're growing rather quickly. I come from a drug discovery background. My team's about 65 people. So we really are a tech company that's doing drug discovery, and my team, if you like, are the users of the technology to apply to projects. So the foundation of the company has come from Google DeepMind, who are next door to our building. So Demis Hassabis, who won the Nobel Prize last year for the AlphaFold technology, is the founder, and our foundational model is the protein structure, protein folding model, which was published as AlphaFold 3 last year. So that's probably the way to think about us as a starting point. But we're a very ambitious company. We've got a number of collaborations now, sort of big collaborations with Lilly and Novartis on very challenging targets. And we're trying to use the core technology and a range of other AI models to apply to very difficult drug discovery problems. So our internal portfolio is focused on cancer and immunology because there's many good targets in that area, but there's also quite good translation and ways that you can use AI to develop, as we heard earlier, biomarkers and how you can measure things more quickly in the clinic. And we have quite a large number of early stage projects that will feed into this growing portfolio. And as I mentioned, we've got significant collaborations with Lilly and Novartis, and we were pleased to extend the Novartis collaboration in February this year, about a year after we first signed the deal. So that deal has doubled in size. So we're using these protein folding technologies to approach drug discovery, I guess in a simplistic way, as if the protein ligand structure is a crystal structure or a cryo-EM. So we get the prediction of how a molecule is binding to any protein or protein complex in a minute or so, instead of, a year in the lab to get the first structure and then a week or two to get any additional structures. And I think, moreover, the protein folding technology is exactly that. It's much more flexible, and we can uncover allosteric pockets, cryptic pockets with predictions that we can then validate in the lab, which is quite difficult to do from static crystal structures where you freeze out a single conformation. This allows us to look at very challenging targets like transcription factors that are intrinsically disordered, because what we see is that with the right ligand, the protein folds around the ligand and becomes ordered. So if you look at an AlphaFold prediction in the AlphaFold database, you see many proteins look like spaghetti, and that's because as a single protein, they're not folded. But if you put them in the right environment, in silico, with the right protein partners and with a ligand, they then fold. And so you've got a signal that that ligand would actually work against that target. And in AlphaFold 3, we can include many other things into that prediction. You can use nucleic acids. Again, the transcription factors, you can add the DNA or RNA. You can look at cofactors, post-translational modification. Sometimes a phosphorylated protein will be entirely different in its fold than one that's not phosphorylated. So there are many signals that you can see in silico that you can then follow up on in the lab. So I mentioned AlphaFold 3 was published in May last year and has, I think, broad adoption. I think people are using these technologies extensively to help them with their structural biology. And we see new publications weekly where people are using AlphaFold 2 or AlphaFold 3 as part of a workflow. I'm lucky enough to be an author on the AlphaFold 3 paper, and I get around 120 citations a week, which is quite good for my H factor. So this had a lot of impact. And I think this model brings a lot of capabilities to do biology. So you can start to look at protein structure predictions that were not possible before and make predictions. So for example, AlphaFold 3 gets protein antibody complexes right 50% of the time now, which is a big improvement on AlphaFold 2. And our models are much better than this. So that opens up the discovery of biologics. So you can say, you can design a potential antibody and you can work out which epitope it would be binding to. And as I mentioned, you can add in other things like RNA and DNA into a complex and do the in silico experiment to see whether there's a pocket under certain circumstances with this larger complex. We really see AlphaFold 3 as just a point along the road for us, and we've been working on this protein folding continuously since the company was founded. Our current model is much better, a range of problems including protein ligand co-folding, peptide protein interactions, antibody protein complexes and PPIs. And on the right you can see an example where our model correctly predicts the ground truth structure for a ligand. AlphaFold 3 finds the right pocket but gets the orientation wrong. So in the detail of doing a drug discovery project, of course you need it to be completely accurate for your project, otherwise it isn't working. So we spend a lot of time validating what we're doing and selecting the right targets where the platform is working very robustly. And as I said, it's essentially like getting a crystal structure for every in silico experiment that you run. And all we have to do here is put in the protein sequence or protein sequences, any other cofactors, and then a ligand, and we can get that prediction. So it runs very quickly. We can put in 1 million compounds in a virtual screen and get a prediction of whether or not that molecule is going to bind to a certain pocket. And we're continually innovating to get more and more coverage of the proteome to get higher and higher accuracy to any protein system. We just heard about physics-based methods. We've got a physics-based simulation team. We do a lot of long MD simulations, and then we use that data as synthetic data to train a machine learning model. So it's a type of data that one can use rather than wet lab data. And the MD simulations run about 1,000 times faster. So once you've built that machine learning model, you then can reproduce what you would get in a very expensive MD simulation. And I've already mentioned protein-protein interactions where we've got a much better prediction. So we can now try and discover new biology. You could say, here's my protein of interest that I'm very excited about, and I want to find something that binds to it that might be an effector, and we can predict which proteins might bind to that high-value target to help us, for example, to design molecular glues against that target. So there's a quick video here. This came out with the AlphaFold 3 paper. It shows the sort of thing that we can do, the sort of signals that you're looking for in silico. This is TIM3. This is a published story. And you can see that these two tryptophans move significantly to form a pocket that's not present in the apo protein. So that signal would say this might be a pocket. If you imagine a new protein that's not published, if you're doing a virtual screen in silico, if you see these sorts of protein movements, that might be a real thing. We can investigate whether that's actually a binding event. I think, just to close, I think one of the most exciting innovations that we're using now as part of our platform is de novo design. So another large area of research that we've had since the company was founded is on predicting other properties, so binding affinity and other ADMET properties like log-D or clearance, permeability. And we're making a lot of progress, particularly with binding affinity, using very large amounts of data and training machine learning models to tell us whether a particular ligand will bind to a particular protein in a completely agnostic perspective from which pocket. You're not having to tell it what the protein structure is or where the pocket is. it just makes a prediction this molecule should bind to this target. And we can use this in virtual screening, we can use it in SAR within projects, and we can use it in de novo design. So this algorithm just creates a molecule out of thin air, atom by atom, and places it somewhere on the protein in a region that it believes is a pocket. And we then need to go and make that compound in the lab, which is expensive and time-consuming. But we're seeing quite remarkable success rates. So there's 7 different projects here that we ran last year. Some of these projects are projects that were given to us by Lilly or Novartis, so we don't get to choose those targets. They're difficult projects. And we've synthesized, in most cases here, somewhere between 5 and 20 compounds in the lab, and we're getting, on average, something like a 30% hit rate. So we're getting hit compounds coming from just synthesizing 5 molecules that then bind to a pocket on the target of interest, which, as you can imagine, is a much quicker and cheaper way than running a high-throughput screen or a fragment screen or even a virtual screen. And this has become a workhorse method for us. These compounds are completely novel. They're not in catalogues. They've been designed by the AI system, so they bring that advantage of being completely novel start points. And you can use the technology to find the pocket. You can just investigate proteins and say if the model is putting compounds consistently in a certain region of the protein, maybe that is a pocket that is allosteric, for example. So this is just a quick taste of what we're doing. There's lots of other areas of research, and we may get into some of that on the panel. So I'll stop there and thank you for listening.